I'm really happy to be here to share with you what I have learned about multi-agent paradoxes in the past few years. And these paradoxes usually in the literature are also called the extended Wegener-Strand no-go theorem. So when you see these two names, usually they mean the same thing. Previously, Renato told us, well, he started to talk about one of the most famous extended Wegener-Strand argument, which is the Verheugen-Renner one. And in this talk, I will introduce to you the other famous one, which is the local friendliness theorem. A major difference between the Verheugen-Renner theorem and the local friendliness theorem is that as Renato mentioned in his talk, the Verheugen-Renner theorem is a lot about how agents perform reasoning in quantum experiment, while the local friendliness theorem is formulated more from this God's eye view, and it's more about what's out there, what exists out there in reality, rather than how agents should do reasoning. Okay, so the local friendliness theorem was initially proposed in this paper, and then these ones are some further developments of the theorem. In this talk, I will mostly follow the presentation in the review paper of various extended Wegener-Strand theorem I wrote with David Schmidt and Matt Liefer, because in the review paper, we tried to use a unified framework to talk about all kinds of extended Wegener-Strand theorems, and we tried to make the presentation pedagogical. So before I get into the local friendliness theorem, let's first recap a particular version of Bell's theorem, which David mentioned this morning. So this version was proposed by Hardy. And I want to mention this particular version is because later, as we will see, the quantum correlations used in this Hardy's proof of Bell's theorem will also be used later in my presentation of the local friendliness theorem. And I believe tomorrow you will see these correlations being used again in the Verheugen-Renner theorem. So notation-wise, in my talk, in my diagrams, I don't distinguish between single-wired wire or double wire. So everything will be single wire, either it's quantum, GBT, or classical, because this distinction is usually clear from the context. Right, so this is the schematic diagram for Bell's experiment. In the Hardy's proof of Bell's experiment, the initial quantum state shared between Alice and Bob is this one, the Hardy state that David mentioned this morning. So this is the expression of the Hardy state. All the measurements in the Hardy's version of Bell's theorem, all of them have binary settings and binary outcomes, meaning that they can take the value either 0 or 1. In particular, the measurement setting, when the measurement setting is 0, for example, when x is 0, Alice will measure her share of the bipartite system in the 0-1 basis, which is also called the computational basis. And when x equals 1, Alice will measure her share of the bipartite system in the plus-minus basis. And the same for Bob. So when y equals 0, Bob measures his system in the 0-1 basis. And when y equals 1, Bob measures his system in the plus-minus basis. Then quantum theory will make the following predictions. First, in the runs where x equals 0 and y equals 0. So these are the runs where both Alice and Bob, they measure their share of the bipartite system in the computational basis. So in this case, quantum theory predicts that it is impossible for both of them to get the outcome 1. And this is because if we look at the expression of the Hardy state, as we can see, there's no 1-1 term. So so the probability of getting the outcome to be both 1 is 0. And then in the case when Alice measures her share of the bipartite system in the computational basis, and when Bob measures his share of the bipartite system in the plus-minus basis, quantum theory makes this prediction because if Alice's outcome is 0, we can see that since they share the Hardy state, when Alice obtains the outcome 0, Alice will steer Bob's state to be a plus state, because these are the ones corresponding to the case when Alice's outcome is 0. Therefore, it is impossible in this case for Bob to obtain the outcome minus. Therefore, this joint probability is 0. And then since the Hardy state is symmetric in AB, so in the opposite case, we get the prediction that if Bob obtains outcome 0, then Alice cannot obtain the outcome minus. Finally, in the case when both of them measure in the plus-minus basis, this is a little bit hard to see directly from the expression, but if you do the calculation, you will find out that it is sometimes possible for both of them to observe the outcome minus because this joint probability is, does not equal 0. Okay, so all of this so far, we are just using quantum theory, in particular using the Born rule to predict the observed outcomes in the Bell's experiment. As David mentioned yesterday, in Bell's theorem, we have the assumption called classical realism. Specifically, it says that there exists some hidden variable lambda that can specify the outcomes of all possible measurements, no matter whether the measurement will be performed or not. So here, I used the assumption of determinism in the sense that lambda will deterministically specify the outcome, but as David mentioned yesterday, this assumption can be relaxed. It doesn't affect the proof of the Bell theorem. So for simplicity, I just assume determinism. Furthermore, in Bell's theorem, we assume that an outcome can only depend on its local variables. So Alice's outcome A can only depend on X and lambda, while Bob's outcome B can only depend on his measurement setting Y and lambda. And here we can use A0 to denote the value specified by this function given a particular value of lambda and when X equals 0. And then we use A1 to denote the value specified by the function and a given lambda when X equals 1. And similarly, B0 for Y equals 0, B1 for Y equals 1. So given a lambda, we can it specifies the values of all 4 outcomes. However, in a given run of experiment, since the measurement in the 0-1 basis is incompatible with the measurement in the plus-minus basis, so in a given run of experiment, only one of the value between A0 and A1 can actually be reviewed by the measurement. And similarly, only one of the value between B0 and B1 can be reviewed by Bob. However, since lambda specifies the outcomes of all of these measurements, we can get a contradiction from these quantum predictions. So how? First, from the first equation, so this is about the runs where X equals 0 and Y equals 0. So this is about the ones, so here the relevant outcomes are B0 and A0. And this equation implies this implication because when B0 equals 1, since the joint probability is 0, so it means that A0 cannot be 1, so A0 must be 0. And then, and also this implication holds for any lambda because this is a joint probability distribution. It doesn't really refer to your lambda. And then for the second equation, this is the case where we can review the outcomes for A0 and B1 because it's X equals 0 and Y equals 1. So this says that if A0 equals 0, B1 must be plus because B1 cannot be minus. And then similarly for the next one, it says that when A1 equals minus, then B0 must be 1 because here Bob's outcome cannot be 0. Okay, since all of these implications holds for any lambda, so we can chain the implications together. What do I mean by that? What I mean is if you start with A1 equals minus, it implies that B0 equals 1. And then B0 equals 1 further implies that A0 equals 0. And then A0 equals 0 further implies that B1 equals minus. So by chaining them together, at the end, you will get A1 equals minus implies that B1 equals plus. However, this contradicts with the last equation here, because this one says that when they both chose the measurement, when their measurement settings are both 1, it is possible for their outcomes to be both minus. So A1 equals minus does not imply that B1 equals plus. B1 can be either minus or plus. So we have a contradiction. And here we just finished the Hardy's proof of Bell's theorem. Does anyone have any questions at this stage? Okay, good. So the assumption we used to get the contradiction, one of the assumptions is the classical realism assumption. This can also sometimes also called the hidden variable assumption, and you can conceptualize it as the assumption of the ontological models framework or the classical causal modeling framework, as David mentioned yesterday. So some interpretations reject these strong kind of realist assumptions. For example, the interpretations with an quite strong operationalist or empiricist flavor, notably the Copenhagen interpretation and the interpretations that are similar to it. And you can find a summary of these kind of interpretations in this article. And this sentence mentioned by David yesterday can be thought of as a typical response of these interpretations to Bell's theorem. They say that unperformed experiments have no results. So what do they mean by that? So what they are referring to is the fact that these four measurement outcomes cannot actually be observed in a single run of experiment. Because in one run of experiment, Alice makes one measurement and Bob makes another measurement. You only get two measurement outcomes. Furthermore, as we mentioned earlier, the 0-1 basis measurement and the plus-minus basis measurement, they are incompatible. So it is impossible for them to observe all four outcomes in one run of the experiment. Therefore, for these interpretations, either A0 or A1 is meaningful, not both. And either B0 or B1 is meaningful, not both. Therefore, for them, you cannot chain these implications together, because by chaining these implications together, you require that A0, A1, B0, B1, they are all meaningful at the same time. Is there any question about this response to Bell's theorem? Okay, cool. So, what if we can come up with an experiment where all four measurements are actually performed in a single run? This is indeed possible if we combine the elements from Bell's theorem, from Bell's experiment and Wegener's friend thought experiment that Renato mentioned this morning. And this idea was initially proposed by Chancellor Bruckner back in 2015, and eventually it led to the local friendliness theorem developed in 2019. So now I will present the version of the local friendliness theorem that uses the Hardy state, and this version was originally proposed by in this paper. So in the local friendliness theorem, here we first have two observers. We name them Charlie and Debbie. They share Hardy state. And for Charlie and Debbie, neither of them has a measurement choice. In particular, in every run of the experiment, they always perform the 0-1 basis measurement on their share of the bipartite state, their share of the bipartite system. Then we will add the elements from Wegener's friend thought experiment to this experimental setup. In particular, now we assume that Charlie is perform his measurement in an isolated laboratory. And then, as Renato mentioned this morning, if we further assume that quantum theory is universal in the sense that it can also apply to macroscopic systems, including agents, including observers, then according to quantum theory, an isolated system, it will evolve unitarily. So Charlie's measurement process in this laboratory just can be modeled as a unitary. Then Charlie has a friend, Alice, who is outside of his lab. So Alice has measurement choice, unlike Charlie, who doesn't have a measurement choice. Alice's measurement choice is denoted by X. Here we also assume that both the measurement choice and her measurement outcomes are binary. Then, furthermore, we assume that Alice, we call her a super observer because we assume that she also has the capability to perform quantum operations on this laboratory where Charlie is in. For Alice, when her measurement setting x equals 0, we just ask Alice to simply open the door to Charlie's laboratory, ask for Charlie's outcome, and report Charlie's outcome to the world. And when x equals 1, as Renato mentioned this morning, here we can ask Alice to perform the inverse of the unitary on Charlie's laboratory so that Alice will reverse Charlie's measurement process, restore Charlie's share of the bipartite system to the initial state, which is before Charlie's measurement. And then Alice herself can take Charlie's share of the bipartite system and do a measurement in the plus-minus basis. Okay, so that's what Alice will do. Is there any questions about? Okay, good.
The super observer decision on what to do depends on the X measurement.
Exactly. So X is Alice's measurement choice, and when X equals 0, she simply reports Charlie's outcome, and when X equals 1, she will do this complicated quantum operation, the inverse of the unitary.
A, the wire A, it's quantum or classical depending on X?
Sorry, A, it's always just a classical outcome. Okay. So, yeah, so here C denotes Charlie's outcome, A denotes Alice's outcome, X is Alice's setting. Okay, then on Debbie's side, the experimental setup is exactly the same. Debbie has a friend, Bob, who is also a super observer, and when Y equals 0, which is Bob's measurement setting. So when Bob's measurement setting is 0, Bob simply reports Debbie's outcome to the world, and when Y is 1, Bob will reverse the measurement of Debbie's and return the state to the initial state. Then Bob takes the state and perform another measurement in the plus-minus basis. Cool. So this is the experimental setup. Now we can, I think you can already realize that first, the 0-1 basis measurements are actually performed in every run of the experiment, because Charlie and Debbie, they do not have a measurement choice. They always do the same measurement. And the plus-minus basis measurements, now they are actually performed in all runs of the experiment whenever X equals 1 and Y equals 1. So in these runs, in the runs when both X and Y equal 1, all 4 measurements are actually performed.
Like, how can you verify from the point of view of Alice or Bob that C or D actually performed the experiment?
Right. So David Deutsch had this protocol where Charlie, for example, after the friend made the measurement, he can issue a note to the world saying, I made the measurement, but he would not tell the world what precise outcome I get from this measurement.
Okay. And that doesn't break any
uncertainty principle or something. Yeah, because he did not tell the world what outcome I get. He only says, I did the measurement, I saw an outcome. Although there's also some controversy around this protocol, but yeah. If you're interested, we can talk more later. Yeah, okay. Cool, so since in these runs, all 4 measurements are actually performed, so we expect to derive a contradiction just like in Hardy's, but where we do not need to appeal to the assumption of classical realism or the existence of the ontic state.
Sorry, just an easy thing I didn't understand. The X measurement of Charlie and the Y measurement of Bob is equivalent to a coin, a toss of a coin?
Yes.
Right, okay.
You can, yeah, exactly. You can, they are, or they can freely choosing, for example, as David mentioned, according to the digits of pi or, yeah.
Okay. It's not quantum, okay.
Yeah, it's just some measurement choice. Okay. Right, so indeed we can do that. So how do we do it? First, recall that the Hardy state had this expression. So quantum theory will make the following predictions for the outcome that we can actually observe. In the runs when X equals 0 and Y equals 0, so this is the case where both Alice and Bob just simply report their friend's outcome. They will not do the reversals. In this case, quantum theory predicts that it is impossible for Charlie and Debbie to both observe outcome 1, as we calculated before, because there's no 1-1 term here. And then in the case where Alice simply reports Charlie's outcome, and while Bob performs the reversal and remeasure in the plus-minus basis, then if we do the same calculation as we did in the Hardy's version of Bell's theorem, then we will get this conclusion just like before, which is C equals 0, which is that the probability for C equals 0 and B equals minus is 0, because again, when Charlie obtains the outcome 0, it will steer, he will steer the states on both sides to the plus state, so it's impossible to get the minus outcome. And then in the opposite scenario, we also get the opposite expression. When x equals 1, y equals 0, it is impossible to have a equals minus, d equals 0. And in the last case, when both Alice and Bob reverse their friends' measurement processes and remeasure in the plus-minus basis, it is sometimes possible for both Alice and Bob to obtain the outcome minus. Okay, so all these quantum predictions, they are about the facts that can be actually observed, because all of these correlations can in fact be verified in your laboratory after you finish the experiment. But they are about different runs of the experiment. So we want to convert these two facts about only the runs where both x equals 1 and y equals 1, because as we discussed before, it is only in these runs all 4 measurements are actually performed in a single run. So how do we do that? We use the assumption called local agency. It says that a freely chosen setting is uncorrelated with any observed events that are relevant to the phenomenon and outside the future light cone of that setting. So here the freely chosen setting, so Alice has one setting, freely chosen setting x, Bob has another one, y, and the relevant observed events to the phenomenon are A, B, C, D, X, Y, these 6 events. So first, for Alice setting x, according to local agency, in the case where Alice and Bob perform their measurement in a space-like separated fashion, x cannot be correlated with C, D, B, and Y, because all of these observed events are outside of its future light cone. And similarly, y cannot be correlated with C, D, A, X, because these 4 events are outside of the future light cone of y. Now we will use local agency to convert the facts about different runs of the experiment to the runs where x equals 1 and y equals 1. So for the first equation, since both C and D are outside of the future light cone of x and outside of future light cone of y, therefore, when we change the values for x and y, the probability distribution doesn't change. Therefore, this equation implies this equation. And then for the second one, here we change the value of x, and since both C and B are outside of the future light cone of x, so again the equation, the value of the probability distribution stays the same. For the 1, similarly here we change the value of y, and since both A and D are outside of the future light cone of y, so again it still equals 0. And for the last one, we don't need to do anything because it's already about the runs where x equals 1 and y equals 1. So now, all these equations, these probability distributions are about the runs where all 4 measurement outcomes are actually observed. So now we can chain the implications together just like before and derive that when A equals minus, we will get D must equals 1. And if D equals 1, then this one tells us that C must equals 0. And when C equals 0, this equation tells us that B must equal to plus. So A equals minus eventually implies B equals plus. However, this contradicts with the last equation because here it says A equals minus can coexist when B equals minus, so the implication should not hold. Therefore, we get a contradiction. Is there any question about the derivation?
I'm sorry, I didn't understand going from these equations to this equation. Can you explain that one more time?
Okay, so the basic idea, first, why do we need to go from the left to the right? It's because on the left, these are correlations conditioned on different runs of the experiment. So they are conditional probabilities conditioned on different things. Therefore, without further assumptions, you cannot, they do not constrain each other because they're conditional probability distribution with different conditions. Therefore, what we want to do is that we want to use some assumptions to translate all these predictions to have the same conditionals. to have the same thing that it conditions on. And in particular, we want to translate them to be about the runs where x equals 1 and y equals 1, because these runs are the ones where all four measurement outcomes are performed. Okay, so that's the purpose why we want to do that. And how we do it is using the assumption of local agency. Basically says that for any setting, it cannot be correlated with any observed events that are relevant for the phenomena outside of its future light cone. So here, since for the first equation, both C and D, so first they are outside of X future light cone, so they are not correlated with X. And they are not correlated with Y because they are outside of Y's future light cone. Therefore, when we change the value for X from 0 to 1, and when we change the value of Y from 0 to 1, the probability distribution stays the same. Okay, thanks for the question. Is it clear? Okay, cool. Right, so now we have seen that without assuming classical realism, we can already derive a contradiction, and this is exactly the local friendliness no-go theorem, which says that quantum predictions, in particular the ones made with the assumption of universality of unitary dynamics and the Born rule, are inconsistent with the assumption called local agency. And here I just briefly restated here again. It says any setting is uncorrelated with any set of relevant observed events outside of its future light cone. This assumption does not require the existence of hidden variables because it's only about the relation between a setting, which is an observed variable, and observed events. So there's nothing about hidden variables. Furthermore, if you apply local agency to Bell's experiment, then the consequence of this assumption is simply the no signaling condition that David mentioned earlier, which, again, doesn't say anything about the hidden variable lambda. Therefore, in the local friendliness no-go theorem, this typical response that for an operational list type interpretation will no longer apply because, as we mentioned, in the end, the contradictions are about experimental outcomes in a single run of the experiment where all measurements are actually performed. And so, as compared to Bell's theorem, in Bell's theorem, one could think that all the quantum weirdness is confined to this hidden variable thing, this microscopic thing that no one can actually observe. But now with the local friendliness no-go theorem, in some sense, this quantum weirdness now is no longer just confined to the microscopic things. Even if you only think about observed events, you cannot escape the weirdness of quantum theory. So how, yeah?
I don't understand anything. In the first of the implications from one probability distribution to another.
Yeah, sorry.
In the first implication, you are saying P of C1, D1, D equals 1, condition on x1, x equals 1, y equals 1. Okay. Now you are exactly saying something about unperformed experiments, because there it's saying I am performing 1, x equals 1, and y equals 1, made by Alice and Bob, and C equals 1 and D equals 1 are experiments, as far as I have interpreted this, made by Alice and Bob opening the box. The results on the left, C equals 1 and D equals 1, are results that Alice and Bob can learn only if they open the box.
Yes.
But on the right, we are saying that they do not open the box. So I feel like what's on the right, at least some of them, are exactly statements about unperformed experiments.
So on the right, which experiment is not performed? Can you pinpoint your?
Yeah. I would say that these statements are statements made always by Alice and Bob, because either they open the box, but that's an Alice choice or Bob choice, or it's random. Okay, but either they measure the superposition. Okay, I would say the other basis. Okay. But sorry, they make the reversal. But that's still an Alice and Bob choice. So
I really don't understand why we would say that C equals 1 and D equals 1 are still performed if we are confronting and talking about Alice and Bob's final measurements. You know, all these results like C, D, A, and B are all results by Alice and Bob. Either they open or they don't, but they're still their results. And in one case, they don't do a thing, and I think I don't know if
so
if it's
maybe
clear.
the confusion coming from so C and D they really refers to Charlie and Debbie's results, not Alice and Bob's results.
But x0,
When
x
x
equals
zero, what Alice does is simply allow Charlie to report his outcome to everyone. It's like when you have a friend doing a measurement, and at the end of the experiment, you don't do anything weird to your friend. You just allow them to tell others what their outcome is.
Yeah, I agree. But I feel like we are saying by make the first probability on the left implying the second, we are implying something about two non-compatible observables, because we are saying x equals 0, x equals 1, but how can we derive something from another choice which is not compatible with the other? No, okay, it was a bit chaotic at the end, but I don't know if someone can
I think
help
I
me.
maybe understand your idea. It's like what Alice does in these runs, they are incompatible. So your question is why, when Alice is doing incompatible experiments, we can still say that Charlie and Debbie has the same outcome, no matter what Alice and Bob does.
And
right?
moreover, and
Yeah.
then I finish. And moreover, I feel like we are using the machinery of quantum mechanics or quantum theory only from Alice and Bob's perspective, everywhere. But finally, we say that the measurements are also made by Charlie and Debbie, but we always look from Alice and Bob's perspective. So how can we look from Alice and Bob's perspective and use the machinery of quantum theory and confront x equals 0 with x equals 1 if they are incompatible, measurement devices?
Yes, so how do we do that? It's precisely because we make this extra assumption of local agency. Without this assumption, of course, you cannot say anything about what happened. Well, not of course, but it depends on interpretation. You may not be able to say anything about Charlie's and Debbie's outcome in the runs where Alice and Bob do not allow them just to report to the world. But precisely because we assume this assumption, which is motivated by special relativity, then we can relate the Charlie and Debbie's outcome from the runs where actually everybody can hear the outcomes from them to the runs where they are now not allowed to tell everyone. So it's this assumption that is doing the work, is it?
But would you say that violating this assumption would violate special relativity?
It again depends on what you... Okay, so there are different views
But maybe
about...
it's a question for later. I don't want to interrupt too much. That was the main question, the first one.
Okay, so I will just respond shortly. So some people think that special relativity implies that nothing can travel faster than light, even if we cannot observe them. But for some people, they think special relativity merely implies that only we cannot signal to each other, like only observed things you cannot directly observe faster than light things. They don't. Yeah, so it again depends on what you think special relativity implies. The violation of this assumption may or may not contradict special relativity. Okay.
Thank you.
Cool. Good. Right. So, another thing I want to mention is, in fact, there is an assumption that I have been implicitly using in my presentation of Bell's theorem, and actually in David's presentation of Bell's theorem, and my presentation of the local friendliness no-go theorem. But we will not get into this assumption right now. Instead, I want to present to you a different version of local friendliness theorem, which is formulated in the causal modeling language. And then I will tell you this implicit assumption. So why do I want to tell you a different formulation of this local friendliness theorem? Because as David mentioned yesterday, among the people who reject the assumption of classical realism, there are two types. One takes the operationalist point of view. One takes the operationalist route to say that unperformed measurements have no results. But the other type of people, they still want to stick to the realist route, and they would like to still give a realist account of our quantum experiment in particular using the in particular about the causal mechanism underlying our quantum experiment. So once we learned this version of the local friendliness no-go theorem, we will see that the local friendliness no-go theorem will pose a much stronger challenge to the second route I just mentioned, where it's using causal modeling framework to understand the quantum experiment than what Bell's theorem poses before. Okay, so again, we will recap Bell's experiment, but now explicitly in the classical causal modeling language. Previously, David has been using a circuit diagram to represent the causal structure, but here I will use a different language, which is the directed acyclic graph language, because if you go to the literature on causal modeling, especially classical causal modeling, the DAG language is the most commonly used one. So if we write down a causal structure, a natural causal structure for the Bell experiment, I think most of us will agree that this is the natural causal structure. So here in this DAG, we have nodes and arrows. The arrows represent the cause-effect relations between the nodes. And for the nodes, these triangle ones, we call them observed nodes because they are associated to things that we actually observe in the lab. And then this circular circle one, we call it an unobserved node or a latent node because it represents our causal hypothesis about what's underlying the experiment. For example, here we have the causal hypothesis that there may be a common cause that can explain the correlations between Alice and Bob's outcomes. And in the classical causal modeling framework, this unobserved node must be associated to a classical variable. And then, as David showed yesterday, any correlations that can be explained by this causal structure, or in other words, any probabilities that are compatible with this causal structure must satisfy this factorization condition. And the factorization condition further implies the no signaling constraints on the observed correlations and the Bell inequalities on PAB given XY. So this means that any correlations that are compatible with this causal structure, or in other words, any correlation that can be explained by this causal structure cannot violate Bell inequalities. It must satisfy Bell inequalities. So any classical model with causal model with the Bell DAG cannot explain violations of Bell inequalities, which we already have many experimental evidence that, that the violations do happen. So if you want to stick to the classical causal modeling framework, there are ways to explain the quantum violations, but you'll have to change the causal structure, for example, by adding these arrows. However, again, as David mentioned yesterday, these causal structures, they violate certain important causal principles. For example, the first one will imply there are faster than light causation, the second one will imply ritual causation, and the third one implies superdeterminism, meaning that even though you thought you are making a choice randomly, but in fact your choice is affected by the system you are measuring. Therefore, because these shortcomings of classical modeling framework in explaining Bell's experiment, people come up with non-classical causal models. And the basic idea is that we keep the causal structure intact, but we will generalize the notion of causality. What do I mean by that? So in a non-classical causal models, now the unobserved node is no longer required to always being associated with a classical variable. Then we don't have this factorization constraint on the compatible probabilities because we don't assume that there's a lambda. And so we also cannot derive Bell inequalities on PAB given XY. Therefore, using under non-classical causal modeling framework with the same causal structure, we will be able to explain the violations of Bell inequalities. And more concretely, for example, if you associate your unobserved node with a quantum system, then the constraint on your compatible probabilities will be, so you'll have a generalization of the factorization condition as your constraint on your compatible probability distributions, which is this one. And here, this conditional quantum state is a generalization of the conditional probability distribution. And I will not go into the details, but if you're interested, you can check out this paper. With the quantum system associated to the unobserved node, then we get a quantum causal model. And under quantum causal modeling program, the framework, you can explain any violations of Bell inequalities up to the quantum bound, for example, the Torossian bound for the CHSH inequalities. And furthermore, if you allow your unobserved node to be associated with the GPT, then you can explain violations of Bell inequalities up to the no signaling bound, so including the ones that are beyond quantum theory. But yeah, we still have the no signaling bound. Why? Because as proven in this paper, the independence constraints on observed nodes are still valid, even if you are using a GPT instead of classical theory to describe your causal mechanism. So as we saw, it seems that we have a very powerful and a very versatile, powerful, and very reasonable causal modeling framework, because we can explain violations of Bell inequalities up to the no signaling bound and the no signaling condition, which is the one that we always observe in our experiment, is always reproduced by the causal models. Okay, so far so good. However, here comes our antagonist, which is the local friendliness theorem. So now I will present a version of the local friendliness experiment that is called the minimal version, because in fact, the simplified version of the local friendliness experiment is sufficient for deriving a contradiction. So in the minimal version, the only difference between this one and the previous one is that we no longer have a friend for Bob. On Bob's side, now Bob just does whatever he usually does in a Bell experiment, so he has some measurement choice. Why? According to his measurement choice, he makes a measurement on his share of the bipartite system and obtains an outcome B. And on Alice's side, everything is the same as what we saw before. Alice has a friend, Charlie. And when x equals 0, Alice simply reports Charlie's outcome. And here, for notational convenience, we also just set Alice's outcome to be the same as C, so that meaning that Alice just simply copies Charlie's outcome. And when x equals 1, we allow Alice to do whatever she wants to do on Charlie's lab including the inverse we mentioned before. Okay, so previously we saw that under the quantum causal modeling framework, or the GPT causal modeling framework, with the Bell DAG, we can explain quantum correlations in the Bell's experiment. Now, what will you propose as the causal structure that can, for explaining the local friendliness experiment? Any suggestion? The right side should be the same. You mean exactly the same thing? This one. Sorry. Oh, right. You mean Bob's side. Right. Okay. Yeah. Okay. Bob's side. They should. And how about the left side? Yeah.
We need to remove x from A and we put it into another variable. That is, well, A is named C and we put x into Alice further down.
Let me just either chalk. Oh yeah. So on the right hand side, we all agree that it's the same. And then so you said, sorry, can you repeat again? What?
It's like the quantum common cause, it goes to C.
C.
X goes to A. C has to go to A also. A can output something.
Right, A is the outcome of Alice. Okay, does everyone agree with this?
Shouldn't x go to C, because whether or not Alice can copy his condition on C?
Okay, so you suggest x go to C, okay? And anything else? Or everybody agrees with this?
You need Charlie's input, no?
Sorry, say it again?
You need Charlie's input, no? Because C is the output.
Are you suggesting adding something or removing an arrow? I'm not sure.
Oh, no, sorry.
Okay. Okay, does everyone agree with this? There. Right, so you're suggesting adding this arrow.
Well, I'm suggesting that there's no fundamental reason why it should be there.
Yeah, now we are just discussing. So kind of for you, you think there's no fundamental reason that this arrow shouldn't exist. Okay. Any other suggestion? Uh-huh.
Could we add an arrow from A to C? Because
The opposite one. Okay, good. Right, so now I have all the arrows that everyone wanted to add. Is there anything? Uh-huh.
So I wouldn't be sure that the arrow from X to A is necessary, since the arrow from X to C already defines what will be the outcome. From C will define the outcome of A.
Uh-huh.
So I wouldn't say that from X to A would be necessary.
Okay, so you want to put a question mark here. Yeah. Okay, now let's see. The one that I proposed is this one, and let's see what are the difference. First, I agree with you that we should have an arrow from this one to A, because, for example, in the case where Alice reversed Charlie's outcome, Alice can directly take the quantum system herself and do another measurement. So I do agree that we need this arrow. So why? Oh yeah, and I think we also need the arrow from X to A, because, for example, in the runs where Alice, as I said, when Alice reversed her measurement, so kind of Alice's outcome depend on her setting, whether he choose to do this or do that. Therefore, I think this arrow should exist. And why do I don't have these arrows? In the experiment, it can be performed in a way that Alice chose her measurement setting way after Charlie made his measurement. So if you have this arrow, you are implying that you can do ritual causation. You can influence what happened in the past. That's why I don't have this arrow, and similarly, for the same reason, I don't have this arrow, because they both imply that you can influence the past. Okay, so this is the causal structure that I think is the most natural one to explain the local friendliness experiment, and we call it the LF deck. Let's see what kind of constraints it imposes under the GPT causal modeling framework. So it says that these two correlations, they will constrain each other, because, in fact, so I will not present the derivation, but if you believe me, this causal structure under the GPT causal modeling framework implies that there will be monogamy relations on P ABC given XY. And particularly, it implies that the correlation between Alice and Bob's outcome will constrain the correlation between Alice and Charlie's outcome. For example, they constrain each other, not just one constrain the other. For example, if Alice shares a very strong correlation with Charlie, then Alice cannot share a very strong correlation with Bob. And indeed, in the local friend experiment, in the case when x equals 0, Alice can just simply copies Charlie's outcome. So they do share a very strong correlation. And the requirement that when x equals 0, Alice just simply copies Charlie's outcome, it further implies the so-called local friendliness inequalities on PAB given xy. So let's just see a concrete example where all the settings and the outcomes are binary. So this is an example of a monogamy relations on PAB C given xy. The first term describes the correlation between Alice and Charlie, and the second term is the one we saw yesterday in David's lecture. It's a term appears in the CHSH inequalities, and it describes the correlation between Alice and Bob. So individually, the first term can achieve the maximum 1/2 because the probability can achieve maximum 1, and we have a half in front. And the second term, again, it's a probability distribution, so its maximum bound is 1 without any assumption. So for together, the maximum value is 3/2. But here they are upper bounded by 5/4, meaning that there is a trade-off between these two terms. And in the case where A equals C, whenever x equals 0, this equation, so this term, this probability will be 1. So this monogamy relation will imply the CHSH inequality we saw yesterday. And this is a special case where the local friendliness inequality coincides with a Bell inequality. However, in general, the local friendliness inequalities are strictly weaker than Bell inequalities. Or in the polytope language, it means that a local friendliness polytope can be a strict superset of a Bell polytope, meaning that it is harder to violate a local friendliness inequality than to violate a Bell inequality. And this also implies that any violations of local friendliness inequalities are also violations of Bell inequalities, and are therefore Bell non-classical, as well as non-classical in the sense of contextuality that David mentioned yesterday. So studying the extended Wigner's friend phenomena is essentially also studying non-classical phenomena. Okay, so we just saw that using this causal structure under the GPT causal modeling framework, it implies monogamy relations. Furthermore, it implies the local friendliness inequalities on PAB given XY. Therefore, any GPT causal model with the LF deck cannot explain any violations of local friendliness inequalities. However, if we do a quantum experiment, for example, the Hardy correlations we saw before, it will be a violation of the local friendliness inequalities. And if you want to know more details about how to quantumly violate these inequalities, you can check out this reference. So what can we do? Like, how do we explain the violations of local friendliness inequalities? Well, the first thing you can do, just as before, is to change your causal structure, for example, by adding these arrows. But as mentioned before, these causal structures contradict with certain important causal principles that we would like to hold on to. For example, no superluminal causation, no ritual causation, or no superdeterminism. And thus, it shows that if you want to use the non-classical causal modeling framework to explain the local friendliness violations of local friendliness inequalities, you may have to, you will necessarily have to give up one of these causal. You will necessarily have to have these consequences. One of these consequences. Just to summarize. First, we saw that we can explain Bell inequality violations by invoking a quantum common cause in the Bell deck. But no quantum or GPT causal models with the LF deck can explain any violation of LF inequalities. And explaining by modifying the LF deck always leads to contradictions with crucial causal principles. So the local friendliness thought experiment poses a much stronger challenge to causal modeling program than Bell's experiment, because we are literally sent back to the conundrum we had earlier when we only had the classical causal modeling framework and the Bell's experiment. So now I will come back to the implicit assumption that I have been using before. So in this derivation of local friendliness no-go theorem using the causal modeling language, the implicit assumption I've been using is that there must exist the joint distribution over P, A, B, C, give, X, Y, because this is what gives us the monogamy relations. But why does this distribution have to exist? For example, quantum theory doesn't tell us that it has to exist. And in the experiment, we can never verify this distribution because sometimes Alice will inverse Charlie's measurement, erase all the records of Charlie's outcome. Therefore, at the end of the experiment, we cannot collect the data to verify it. In the literature, the assumption that is used to motivate the existence of this joint distribution is called the absoluteness of observed events. It says that any observed event is single and absolute. It is not relative to anything or anyone. One way to understand this assumption is that although we do not have to assume that unperformed experiments have results, but here we do need to assume that performed experiment must have results. And a measurement outcome from this performed experiment must be single and absolute. For example, it cannot be in many worlds where you will get many outcomes. Also, it cannot be like in the Cubism interpretation where a measurement outcome is only meaningful for the observer who observed it. And it also cannot be like in relational quantum mechanics where the measurement outcome is only meaningful for the systems that interact during the measurement process. So, as I also mentioned, this assumption is in fact also needed for Bell's theorem and in fact any other theorems about our observations in physics, chemistry, psychology, or biology, because otherwise how do we even conclude anything from our observations? And the last point I want to make, about this assumption is that, in particular, in the local friendliness no-go experiment, this assumption allows us to simply assign a classical variable for Charlie's outcome, even if its record may be erased afterwards. And tomorrow, we will actually talk more about this lecture. And similarly, in our previous derivation of the local friendliness no-go theorem, this is the assumption says that in the runs where x equals 1 and y equals 1, all these 4 outcomes, they do actually exist. And each of them is single and absolute. They are not private, not relative to a specific wave, branch of the wave function, not relative to, say, a specific measurement interaction. We can chain the implications together and derive the contradiction. Okay, so the final slides is the summary of the 2 versions of the local friendliness no-go theorems we have seen today. They use different assumptions, but they are related. For example, the AOE assumption is implicitly assumed in the non-classical causal modeling framework, and the local friendliness stack can also be motivated using relativistic assumptions. And if you are particularly interested in the causal modeling program, there's actually another way to motivate this local friendliness stack, which is called using the assumption called the no fine-tuning, and you can check out in this paper. And the last thing is that, in fact, since we can use, for example, these assumptions to derive local friendliness inequalities, which can be used to contradict with what we might observe in the experiment. So the local friendliness no-go theorems can actually also be formulated in a theory-independent way, just as Bell's theorem, as David mentioned yesterday. Because instead of assuming the validity of quantum theory, we can just contradict these assumptions with the potential experimental statistics. And then we don't have to, then even if in the future we have some other theory governing our reality, as long as the experimental statistics violates local friendliness inequalities, we know that these assumptions cannot be simultaneously true. Okay, thanks. Questions?
How confident are we in the local friendliness setup that we can perform this U-1 operation?
Right. It depends on what you think qualifies as an observer, what you think that qualifies as a measurement process. For example, in the first paper that proposed the local friendliness experiment, they actually did the experiment where a friend is just a qubit. And if you think that, for example, in relational quantum mechanics, I think any system that participates in some interaction can be a measurement device or can be thought as an observer, then this super simple experiment, well, it's not very simple, but where you only uses qubits already gives you experimental evidence for the violations of local friendliness inequalities. But if you have higher requirements for what can be counted as an agent, for example, Renato said an agent at least should be able to make predictions, then the experiment will be a bit harder. But, so let me just actually go back to right here. So I cannot point for some reason. So this paper, where they actually provide a very detailed experimental analysis about, experimental estimation about what kind of resources we will need, how long it may take humanity to be able to perform a local friendliness experiment with a quantum computer running an artificial intelligence that just as intelligent as human who could do reasoning, and then, yeah, maybe we'll observe the violations of local friendliness inequalities there.
Thank you.
Yeah.
I wanted to ask 2 questions. The first one is simple: are directed acyclic graphs like isomorphic to the circuit representations?
The circuit representation can be more general, especially in the quantum case. In the classical case, if you just think about simple classical theory, they are equivalent, the circuit representation and the DAG. But if you consider some specific classical theory, like for example with symplectic structure, as Rob mentioned yesterday, then I believe the DAG will also be more general than the simple, the circuit formalism will also be more general than the DAG.
Still, the two, they have the same causal assumptions, like no retrocausal stuff and blah, blah. Right?
Okay. Sorry, when I was comparing circuit and DAG, actually I was not assuming any.
Okay, just the formalism,
yeah, just the formalism. I was not thinking about these assumptions.
Yeah, and the other is, like you seemed pretty confident about not giving up AOE, while I know there are some recent development that say, yeah, maybe we should, or what about that?
I'm not particularly confident
Okay.
because I also would like to hold on to no ritual causation, no superluminal causation, no superdeterminant, all these assumptions. So at perimeter, what we thought was, let me just quickly go to the slides. Right. So one particular direction that maybe we could go is that previously when we go from the classical Bell DAG to the quantum Bell causal modeling, what we did is we kept the causal structure intact while updating the notion of causality. And I think now what we needed to do is, well, that's also, this is the research program of Rob Speckens. So going from local friendliness DAG to a better causal model that can explain the local friendly experiment, we need to keep the causal structure intact while updating the notion of both causality and inference. And if you want to know more details about what we mean by updating the notion of both causality and inference, you can check out this paper. So back to your question about AOE, what it means is that we will give up on AOE, but we actually will not give up on the absoluteness. Instead, we think that when an observed event is absolute, it doesn't necessarily mean that it must be represented by a classical variable. It doesn't necessarily mean that the event is described by a set. It may be, we may be able to come up with something that still have the absoluteness, the idea there, but it's not classical.
That's exactly the question that I was going to ask you after, like, how can you do that without, yeah, okay.
Right. Okay, thanks.
Thank you. Thank you for the lecture first. Then I have a question about, okay, you showed this contradiction where you rule out counterfactuals, right? And then my question is, since we are ruling out this assumption, we are making kind of a weaker assumptions in LF inequalities, and then it turns out that the polytopes that you found, they are harder to violate. Well, the inequalities are harder to violate. Then is the main assumption that is this the main reason why it is harder, or is
yes, exactly. It's precisely because the assumptions needed to derive local friendliness inequalities are strictly weaker than the assumptions needed to derive Bell inequalities. That's why, the resulting polytope can also be strictly bigger.
Okay, yeah. So it is relying in the fact that we rule out the assumption of counterfactuals. That's the main question.
I would put it more like because we don't assume classical ontic state, the hidden variable. Because in fact, in terms of counterfactuals, you could argue that in the assumption of local agency, someone may still say that there is counterfactual. Hey, where's look? Right, because we are comparing. Because we are comparing the runs with different settings as
that's true.
Mentioned earlier. So it's not completely without using any counterfactuals, but the kind of counterfactuals needed in the local friendliness no-go theorem is not as strong as the ones we needed for Bell's theorem.
Okay, and then I have a question also there. So you said that, okay, you showed how this leads to a contradiction using quantum mechanics. But then, okay, if we assume, I'm okay. No, you just answered that actually.
Okay.
Yeah, because it was about the counterfactual that you said that we are actually doing different experiments.
Yeah.
Yeah, sorry.
Cool. Thanks.